Welcome to lab number 4, spring 2020 semester for computer-assisted mechanisms. You're going to notice now, with the new reality and the shop being closed off, that the labs are going to look a whole lot like the lectures do. So, I've been kind of racking my brains trying to figure out ways that we can do kind of live stuff without actually having cars to work on. So, what I've done is I've decided to use cars, in my family or whatever, and do whatever I can on them without access to everything. I will pick up some additional tools. I don't know when you're looking at this video, but Thursday, and those will help some. But for right now, we'll just work with what we have and see how far that gets us through the semester. Hello again. Well, we no longer have access to the shop, so I'm going to have to do things a little bit different now. So what I have is this data recorder that I'm going to plug into this 2018 Ford Explorer, and I'll take the car for a ride, and when I get back, I'll go through the data with you and see what we captured and talk about it a little bit. Here's the data recorder we'll be using. It's made by Launch. We have a little scan tool, the same name. Just plugs into the data link connector, and it records data, and then you have to bring it back, hook it into a computer, with a USB cable, download the data from the recorder into the computer, and then we can look at it. So we'll plug it in, we'll put some miles on the vehicle. There is no issue with the vehicle, and I'm not sure that I'm ready to break the car for this lab. We'll see. But we'll see how many different parameters we can capture and what we can look at. So I've taken a nice long drive, probably about an hour and a half, and I've recorded a lot of data. And unfortunately, some of this data is just duplicate. In that long of a drive, you see a lot of the same things. So I'm trying to come up with things that we can look at that we can learn something from. So I do have a list here that I'm going to work off of. So let's start with the simple stuff. I'm going to, share my screen here, and we will launch the, hang on a minute, let me get that out of there. Okay, now let me share my screen. All right, and this C recorder here is what we're interested in. This is the software that, comes with the little data recorder thing. You can actually download this, it's free, and if you're really interested, I can send you the file that we're working off of here. So just kind of look around here. This is not great software. I can't find any way to tie vehicles to users and things like that. So we'll just kind of dive into this here. So I'm going to click on Data Stream and select this number 2 here is the recording we did, and see what we have available. Hopefully you can see this clearly enough on the video. So this car doesn't have any issues. So you can see here there are no DTCs stored in this ECU. The malfunction indicator lamp is off. And then there's a list of the various monitors that are supported. And these are things we're going to talk about in the lecture. We have the misfire monitor. This car does support misfire monitor. That's pretty much mandatory nowadays. I don't know what happened there. The fuel system monitor, so rich lean basically if the fuel trim goes out of whack. Comprehensive component monitoring, which is kind of everything else. Compression ignition monitoring is not supported. You can see that would be a diesel. Misfire monitor. Now it's listing the things that are ready, and so what's weird about this is it shows some things ready that don't exist on this car. So we have EGR and or VVT system monitoring supported. No, but we look here and it says yes on ready. So anything that's not listed as not ready, I guess, shows up as a yes on ready. It's a little weird. So what's available on this car? Misfire monitoring, fuel system monitoring, comprehensive component monitoring. Um, you know, we do have catalyst monitoring supported, but heated catalyst monitoring, no, this car doesn't have a heated catalyst. It does support the evap monitor, but not a secondary air system monitor. This doesn't have an air pump. It does not have a refrigerant system monitor, but it does monitor the oxygen sensors and the oxygen sensor heaters. Here's a question for you. You can answer this in your report. Why do they lump EGR and variable valve timing together as a monitor? What could variable valve timing possibly have to do with exhaust gas recirculation? I'll give you a hint in the lecture, I guess, but they can be used to accomplish some of the same things. So let's see. Under the list of monitors that are ready, the catalyst monitor has run. Heated catalyst monitoring, like we said, we don't have it, but it just marks it as yes. Evap, O2 sensor heater. So that's just a list of the monitors. What else do we have snagged here? Whether we're in open or closed loop, it tells us what oxygen sensors we have. It tells us this is an OBD vehicle. And right now, calculated load value, engine coolant temperature, fuel trim numbers, engine RPM, vehicle speed, timing advance just for one cylinder, but it's going to be pretty much the same for all of them. Intake air temperature, airflow rate in pounds per minute. So sometimes you see grams per second. This is pounds per minute. Throttle position, oxygen sensor output. We have time since engine start, short-term fuel trims, fuel levels, whether purge is commanded, evap system vapor pressure, which you see right now, interestingly enough, is a negative number, negative 0.14, and it's inches of water, which is a much, much finer measurement than inches of mercury. Water is a lot lighter than mercury, so it's a lot easier to lift it. Barometric pressure, which is pretty close to standard. Standard is 29.92, so it's just slightly low. I didn't look at the weather today. And then this is interesting, catalyst temperature, bank 1 and bank 2. That's something we're actually going to look at in another segment of this. So, these are all the parameters that we were able to capture. I could not choose these at all. It just, you plug the thing in and go drive it, it captures what it wants. I also had no control over this. You see there are 12 trips in here, all with a different number of frames. So what's a frame? For example, trip 1, here's the frame number here, so we've got, this is frame 1 of 858. And I can step through this, right? So I can hit this little arrow here, and we go to frame 2 and frame 3 and frame 4. And if we were watching something like, I don't know, engine RPM, let's find engine RPM, it's here somewhere. As we go along, you'll see it's changing. Or I can just hit play and then just watch it change. You can kind of guess what was going on right now. It's just kind of idling. And now you can see I probably drove away when it got a little higher down the road. Let me stop that a minute. So, just to kind of get the layout here, we have all these frames. I'm not going to try to look at every frame in every trip. We can rewind to the beginning. All right. Another thing we can do is we can look at a data plot. So, the data plot allows us to look at things graphically. And here I can pick which parameters I want to display. So if I only wanted to see, say, short-term fuel trim and long-term fuel trim for both banks, click OK. That's what I'm going to see. And I can see it over time. I can roll this back. You notice the frame numbers going down here and our sliders going back, I can pause it. I can hit play and it moves forward. I can put a locator bar here, and then as we go forward, you know, the numbers, right? So we got numbers here telling us what the value is right at this line here, you know. So let me get rid of that mess. Also, we're seeing, you know, minimum and maximum on each one of these things. So that's something you can look at. I can step through like this. I can hit play, pause. I can choose how many steps we go. Like right now, it's going to go from 442 to 446 when I hit this, because we're saying we want to do 4 steps. I could do it slower. I could do 1 step at a time. It should only go to 447, 448, 449. Don't know if it's necessary for that. We could have it go in huge jumps, you know, 64 steps each time. I don't know if that's even useful. 4 doesn't seem too bad. I can rewind here. I can't do it on this one. You know, pause, like I said, stick a locator in, step through it, watch the values here, you know, change as we step on through. And so we're going to do some of that with some different parameters. You know, so let me move on to the next thing I've got here. What I want to do next thing, look at the mass airflow and engine load, RPM, and throttle position to see kind of how they correlate. So we close this. We'll go to data plot again, and I'm just going to stick with trip number 1 for now, and we'll pick which parameters we want. So like I said, I want the engine RPM, calculated load value, absolute throttle position, and airflow rate from the mass airflow sensor. And let's take a look at that. We'll roll this back to the beginning. That's probably far enough. Let me stick a locator bar in here. Now I can kind of step forward. So interesting, or maybe, you know, not surprisingly, right? If I step forward, I'm going to step forward until our line here lines up with, say, this high spot here. So let me just do that. Step forward. And notice at that spot, right, everything kind of is in a high spot. So we got a peak here. We got a little bit of a peak on throttle position, a little bit of peak on load and engine RPM. So, you know, what happened here, right, is that I stepped on the accelerator, and that accomplished a couple of things, right? It let more air in, so you can see the airflow rate shot up. That, of course, is going to cause the vehicle to accelerate, right? So the RPM comes up, and the load's going to come up naturally. Let's see if that continues to hold true, right? If I step forward a little bit more, you know, now we're kind of in a low spot on everything, right? And we'll start with throttle position, because that's really what's driving this, right? You know, it's hit a low point right there. Our airflow rate hits a low point. Our load then hits a low point, and our engine RPM does. So, you know, throttle position is what's causing the rest of these things to happen. You stomp on the accelerator, naturally, you're going to have more airflow, you're going to have higher load on the engine, and the RPM is going to go up. I'm going to turn off my video here so I can drink my coffee. So that's one set of parameters, see how they relate to each other. Let's, again, I got to turn these off. This software is a little goofy. Here I want to pick 3 more things. I want to show you the relationship between RPM, load, and timing. And I've always told you that timing is mostly based on engine RPM, timing advance. And what I'm seeing on this car, this is a 2018, there's actually even more of a correlation, it seems, between timing and load. So I'll pick RPM, I'll pick load value, and I will pick ignition timing. Take a look at this here. So we have the three. So we'll be really interested in this as it relates to the other two parameters here. So let me get rid of that, and we'll roll it back a little bit here. I'm going to pick frame 1 like we were in before. Roll this back all the way. Oh, now I got to repick the data parameters. Hang on. Goofy software. So engine RPM, ignition timing, calculated load value. And here we are. Now we'll frame 1 or trip 1. We'll roll it on back. That's probably enough. Let me stick a locator bar in here, right? So, here we have our timing advance right now is at, 10. Engine RPM 980. Load, relatively light, 31%. So let's step it forward to, let's see. Let's start by stepping it to a peak RPM here. All right, so I'm going to do that. And let's see, we're going 4 steps at a time. We'll get it through. This looks pretty much a peak. Let me make this a little finer adjustment. See, 29, 28. If we go 1 forward, it's gone down. If we go 1 backward, it's gone down. All right, so this is kind of a peak, and we can see our timing advance at this point is 27 degrees before top dead center. Excuse me. And that is, not at our max. So where does our max occur? We'll continue. Let's instead, let me step backwards till we hit this, what looks to be kind of a high point on load. We'll step backwards here. I'll just hit roll back a minute. And let's see, there's 38, 29, going in the wrong direction, maybe 88% there. All right, so 88% engine load right here. You can see our timing advance is at 41 degrees. Now think about that. Think about what 45 degrees is, halfway between 9 o'clock and 12 o'clock, right? So this crank is quite a ways back from top dead center when that spark fires under these conditions. So let's look now for some low points, right? It looks like we've got some low points, here's a really low point. You shoot for that and see how that correlates. So we'll play it forward a little bit, and we'll look. Right now we're at 82. We'll step it 20, 21, 21. All right, we're going to go back to where it's 20. Yeah. And, our engine load is 20. Our ignition timing is down at 15. RPM is not particularly high, 1130. So see if we can get to this low point here. That's a really low point, so hard to read right now. 38, 0. All right, so we've literally hit 0. My guess, I'm sorry, right here. My guess is that I took my foot off the gas there, and if you look, our ignition timing advance is at 0 here also, which is the minimum. So definitely tied to load. Our RPM is not at the lowest point it's been at. Our lowest, if we look here, is 685, it looks like. So where RPM does play a role in ignition timing, definitely load is a factor. Here's another high point on RPM. Let me try to get to that. So the max is 2928. I don't know where that takes place, but I think we've already seen pretty close to that. Let's see, right now we're at 22. We'll just back it up a little bit. Oh, that was pretty high. 28, 2838 is pretty close to the max, I'd say. So our timing, pretty well advanced here. 32 degrees. Of course, our load is pretty high as well. So, we can see there is a correlation between RPM and timing advance, but there seems to be even more of a correlation between engine load and timing advance. So let me pick some different readings here. Next thing I want to look at the upstream versus the downstream oxygen sensors. We're still going to stay in, trip 1, so that we don't have things. There's just too much data to go through everything. So let me clear these out here, and here we've got. We'll just do one bank to start with, right? So right here, I have oxygen sensor output voltage, bank 1 sensor 2, or bank 1 sensor 1 rather, and bank 1 sensor 2 right here. That's kind of a mess. Let me do that again. So bank 1 sensor 1, and we're going to do bank 1 sensor 2, and notice what we're going to see is voltage out of both of these. So we'll just click those. Okay, let me turn off my camera here, and we'll increase the step rate a little bit here and roll this back. And actually, we don't need to look, I don't think, at individual numbers here too much. You can see it's varying between 0 and almost 9/10 of a volt, 0.87 being the max. Same with bank 1 sensor 2, maxing out at about 0.88, minimum is 0. So what are we actually looking at here? Let me bring this back across the screen so you can see the entire capture. So the most important piece of information here, both sensors are hitting peak almost 0.9 volts, but what's the real difference between these two sensor readings? And the real difference is the frequency, the number of switches. So what do I mean by a switch? Right here is our halfway point, right about, half a volt. I believe 455 millivolts is considered the halfway point on an oxygen sensor. And our peak is running along here just under 1, almost 0.9. And of course the minimum is very close to 0. So when we say switches, what we're talking about is every time it crosses this line here, right? So it's moving upward, then it's moving downward, then upward, then downward, and every time it crosses that center line, right? So every time it crosses right here, we call that a switch, whether it's crossing upward or crossing downward. And these are just too many to count. I don't know if I can try to zoom in. That doesn't work at all. Try this here. Okay, so we are zooming in a little bit, and you can see the big difference here is how more often, the frequency of the switching on bank 1 sensor 1, so this is the one upstream or before the catalytic converter, compared to the frequency of the switching on bank 1 sensor 2, over here it's just kind of hanging out at a steady voltage. So when the catalyst monitor runs, this is what the catalyst monitor is looking at. The difference between switching frequency of the upstream oxygen sensor and the downstream oxygen sensor. They call it an index ratio, so it's really just a mathematical formula comparing switching rates of the two. As long as I have this up, might as well add in bank 2 sensor 1 and bank 2 sensor 2 and just see, what's the difference here. Well, you can instantly see when you look at this which ones are upstream before the cat, right? This one here that's labeled C, and this one here that's labeled A. And D and B here are downstream or after the cat. And it's really easy, obvious, the switching rate here, way, way lower than the corresponding rate of the upstream ones. So that covers our upstream and downstream oxygen sensors. So one other thing I'd like to look at is a little bit of a comparison between the RPM load and the temperature of the catalytic converters. So to be clear, there is no catalytic converter temperature sensor. So the temperature reading that we're going to get is what they call inferred catalyst temperature. It's an inference. It's a calculation or a guess that the computer does, and that's what it's spitting out to the scan tool on what the catalyst temperature is based on all kinds of parameters, including load, RPM, air-fuel mixture. Exhaust is a lot hotter with a lean mixture, but catalysts get hot when they're dealing with a lot of unburned fuel. So obviously I don't have access to the formulas for this stuff. That's proprietary information, but it's calculated rather than directly measured. And why does catalyst temperature matter? A couple of things. We just finished talking about the catalyst monitor, and when we look, we were saying, that's comparing upstream versus downstream switching rates. One of the things before this catalyst monitor will run is the catalyst has to be up to temperature. So one of the entry criteria for catalyst monitor is catalyst temperature. So the computer has to have some way to calculate, is our catalytic converter hot enough to be functional that we can go ahead and run that monitor? If I were able to capture this data when the engine was cold, and I don't think I did, this is, trip 1, and I had literally just started the vehicle. So maybe, way over here at the beginning, it seems to be switching more when the catalyst was cold, when the car first started. And then, of course, when you get down to here, the switching rate is definitely a lot lower. So we may be seeing that here. Don't know if we have enough data to make that judgment, but when the catalyst is cold, it really doesn't work very well. So for the catalyst monitor to run, the computer first has to determine that the catalyst is hot. So let me actually going to pause here a minute if I can. So I don't know if you can tell, I just paused it to get a cup of coffee. Here, let's try a little TV magic, all right? So I'll know whether or not you actually watched this entire video. So we're going to do a little magic trick. Okay, what just changed there? So I'm going to know by your report. If you don't mention that in your report, I know you didn't watch the whole thing. So what just happened there? So I'm going to move on to that catalyst temp thing like I mentioned. let me kill my video and pick some different data parameters. So I want load. Here, let me get rid of these. I want load, I want engine RPM, and we'll go down here, catalyst temperature for the two banks. And let me back this up. That's probably enough. So interesting here, you know, we have two banks, two catalytic converters, but if you notice where there's a high point on the one bank, there's a high point on the other. Where it's going downhill on one bank, going downhill on the other. So I want to know, you know, what does catalyst temperature have to do with engine RPM and engine load? So let's step this forward a little bit, get into it, and let's see, the peak 2928. I don't know if we'll find that. Let's see what this high spot here is. So we'll step that. 23, 2805. Well, that's pretty close. We've got 2805 here, and you can see that clearly corresponds with a high spot. I'm not saying that's the peak. I think it looks a little higher over here, but a high spot in the catalyst temperature, and you know, it says they're both 1356. I think the reason they're exactly identical is because it's using the same formula to calculate, you know, catalyst temperature in both banks. We don't actually have sensors, like I said. If there were actual temperature sensors, I think these numbers would not look so identical. So we really only have to look at one of these to see what's going on here. But notice the catalyst temperature is not constant, right? You can see, right, anytime the load is trending downward, like here, what's happening? The catalyst temperature is trending downward. And, you know, you got a little spike here on load, catalyst temperature starts going back up. So we, you know, look at here, it looks like under engine RPM and load, if we go this way, right? Trying to find a low spot. Yeah, we're going to have to go in smaller steps, maybe. Well, it's relatively low here. We've got, you know, just 21% load. You can see the catalyst temperature is coming downward here, right? If we, you know, step forward to, let me just let it play. I'm looking for these high spots here. Let's see what was going on with those as far as RPM and load. It says our max was 1600, so that looks like a pretty high spot. See if I can step into it a little bit. 1200, 1330, 14, 15, 1585, 1593. All right, we've just gone past our peak. So I think 1595. Notice they're identical again. And so we've just come over a kind of a high spot in engine RPM right here. It's not at our max, but, and relatively high spot on engine load. So not really surprising that our catalyst has gotten warm. So let me talk about, you know, what any of this means or who cares, right? Back in engine performance class, I know I talked about this. When back in the day before heated oxygen sensors, when a car started up, until that exhaust got hot, until that that oxygen sensor temperature came up, I guess the oxygen sensor just plain wouldn't work. So the car would operate in open loop all the time. And before you could do an engine running test on a Ford, you literally had to run the engine at 2,000 RPM for an entire minute, which seemed like an eternity at the time, sitting in the shop. Just sit there and count out 1 minute, 60 seconds. It's a long time. And if you did not do that, if you did not bring the RPM up, get a lot of exhaust flowing through there, get the exhaust temperature and the oxygen sensor temperature up, then the oxygen sensors wouldn't work. It would fail the engine running self-test. So here you can see, as the RPM's coming down towards this low spot, so is the exhaust temperature. And what would happen is you'd get like a Los Angeles freeway with a whole bunch of cars in traffic sitting at idle. The exhaust would cool down. You can see how fast it happens, right? You're seeing it happen here, right? RPM's coming down, exhaust temperature's coming down. And so those cars would sit at idle. The oxygen sensors would cool down. Vehicles would go back into open loop, and then they're not getting the same emissions performance, probably the same fuel economy as they would if they were operating in closed loop. So just a little interesting information here. So let me stop this and just talk to you a minute about what we have to do here. So like I said, I don't have a shop available. I'm going to grab, I'm able to go in today. I can go in only on Thursdays. I'm able to go in and so I'm going to try to grab the Autel, try to grab some stuff out of my office, some of the components that I work with and all that. But it's still going to be limited. So I'm going to be forced to do things like this where it's almost like a lecture format for the lab. So what we just looked at, right, is a car that went out and, like I said, we didn't look at all the data. A car that went out and drove around with a recorder on it, and then we tried to analyze what was happening. This was a vehicle with no problems, no diagnostic trouble codes, no symptoms or anything like that. So everything we looked at, you can assume are normal readings, what a car should read. Also, a 2018 Ford, there's probably 200 parameters we could look at. This software only showed us 30 or so, so we can't see everything, but the main ones, the most important ones, we're able to see. So what I want you to do is, you've watched the video, you can go back through it, you can look at things. So in your report, I give more credit to reports that actually use numbers, that tell me, okay, so when the RPM and load were at this number, timing advance was at this number, just so I know you're actually watching and seeing what I'm saying rather than just running the video in the background saying, yeah, he was saying something about RPM and load, so those numbers, and do the report. I get it. These probably a little harder when we don't have, I don't have a demo to do for you. So do the best you can. I'll take that into consideration. And so as soon as I finish this, I need to start working on the lecture video, which is and isn't going to tie in. We're going to talk about monitors and diagnostics and that. So look for that to come out too pretty soon. And that, of course, you don't do a report. You're doing a test, a quiz on Blackboard. So hope you enjoyed this. Hope you learned something. If anybody is interested, I do have this software. Let's see if I can close this, right? This software is this little C recorder here, by Launch, and it's just crecorder.com. If you download it, I'm pretty sure that I can export the file out of here. and send it to you if you want to look through this stuff yourself. And then you can just play around with it, I guess. So let me stop sharing this again. So it's just me. Anyhow, good luck. Write me a decent report. Email it to me. Again, I really prefer Word documents because if you send me a PDF, it's great, but I like to put notes in it or little comments. I'm going through those. I'll be sending you some back pretty soon. And the PDFs, it's harder to do. So a lot of them I've just been converting to Word before I send them back to you. And, emailing them is much better than sharing them on Google Docs. I mean, if that's the only choice you have, do it, I guess. I can deal with it. I can work with it. But I really do prefer Word documents. Just send as an attachment to an email. And that's how you're going to get back anything that I send back to you anyhow. If you do need, Word, if you don't have Word, if it's expired, I'm pretty sure as an ECC student you have the rights to all that stuff. So you can download or use the online versions. The Office 360. So if you're not sure, helpdesk.ecc.edu, you can put in a request, and I think they'll explain to you how to do that. And the same goes for any of the other Office software, Excel, even Outlook, I'm pretty sure, the whole package. Once again, if you have troubles, if you can't do it, you got to let me know so I can try to help you. My phone in my office is forwarded to my cell phone, so if you call my office, it's going to ring for me. That's all day, every day. I don't turn it on and off. So it's not just during my office hours. So if you have a quick question, I try to get back to the emails pretty quick. Most of you have probably noticed that, but you can call also. All right, we will see you either next lab or for most of you, see you in the lecture.